Welcome to today's paper reading. Today's paper is titled, When is Tree Search Useful for LLM Planning? It depends on the discriminator. This paper, published on the AR14 preprint, examines the role of discriminators and the effectiveness of tree search planning methods for large language models, LLMs. The authors, Ziru, Chen and colleagues from The Ohio State University, the University of Texas at Austin, and Cisco Research, explore how discrimination accuracy impacts the performance of language agents using various planning methods. This paper explores how large language models, LLMs, address multi-step problems within a language agent framework. The framework consists of three main components: a generator, a discriminator, and a planning method. The study examines the practical utility of two advanced planning methods, iterative correction and tree search. A comprehensive analysis is presented on how the accuracy of discrimination affects the overall performance of agents when using these methods or a simpler re-ranking method. Experiments conducted on text-to-SQL parsing and mathematical reasoning tasks reveal several key findings. Firstly, advanced planning methods require discriminators with at least 90% accuracy to achieve significant improvements over re-ranking. Secondly, the current discrimination abilities of LLMs have not met the requirements for these advanced planning methods to achieve such improvements. Lastly, with LLM-based discriminators, advanced planning methods may struggle to adequately balance accuracy and efficiency. For instance, tree search, compared to other methods, is at least 10 to 20 times slower but results in negligible performance gains, which limits its applicability in real-world scenarios. The introduction of this paper highlights the importance of planning in AI, particularly in the context of large language models, LLMs. Historically, AI planning has involved searching for action sequences, predicting outcomes, and selecting the best sequence. This process is analogous to how LLMs handle multi-step tasks, such as mathematical reasoning and code generation. The paper introduces a unified framework for LLM problem solving, which includes a generator, a discriminator, and a planning method. The research focuses on evaluating advanced planning methods like tree search and examining the role of discrimination accuracy in these methods. The study aims to understand how different planning methods perform under varying levels of discrimination accuracy, and whether LLM-based discriminators can effectively assess actions in practical settings. Figure 1 illustrates the generator-discriminator framework for language agents. In this framework, the generator is responsible for proposing partial action sequences, such as SQL queries or Python code. The discriminator evaluates the outcomes of these actions, determining their correctness or effectiveness. The planning method then ranks these actions based on the discriminator's evaluations and manages the interaction between the generator and the discriminator. Both the generator and discriminator are typically instantiated by large language models, LLMs. This framework is crucial for tasks like text-to-SQL parsing and mathematical reasoning, where multi-step problem-solving is required. Recent research has concentrated on advanced planning methods for enhancing the multi-step problem-solving abilities of large language models, LLMs. Despite varying designs, these methods commonly employ a discriminator to assess the agent's actions or planning steps. The discriminator's role is crucial as incorrect outcome predictions can result in suboptimal plans, thereby determining the agent's performance regardless of its planning method. While it is generally believed that discrimination is easier than generation for both humans and AI agents, West et al., 2024, hypothesized that state-of-the-art generative AI models, including LLMs, may not possess discrimination abilities on par with their generation capabilities. This hypothesis aligns with findings by Huan et al., 2024, and Huan et al., 2023a, who observed that LLMs might incorrectly recognize some of their self-generated correct plans as wrong without external feedback. Huan et al., 2024, further note that the benefits of self-correction, an iterative correction method, often depend on high-quality external feedback, such as verifying ground truth labels or test sets for planning loop termination. However, such external feedback is typically unavailable in practical applications due to the unknown nature of new problem solutions and the non-trivial, costly process of annotating comprehensive test cases. The framework consists of three main components: a generator, a discriminator, and a planning method. The generator is responsible for proposing partial action sequences, such as SQL queries or Python programs for mathematical reasoning. For text-to-SQL parsing, the generator uses one-shot prompting with examples retrieved using BM25. For mathematical reasoning, a fixed two-shot prompt is employed. The discriminator evaluates these proposed sequences by formulating the task as binary question answering, generating a yes probability as the discrimination score. Similar to the generator, the discriminator uses one-shot prompting with BM25 for text-to-SQL and a fixed two-shot prompt for math reasoning. The planning method then ranks these actions based on the discriminator's evaluations and manages the interaction between the generator and discriminator. Figure 2 illustrates the three categories of planning methods within our unified generator-evaluator framework. These methods include re-ranking, iterative correction, and tree search. The generator is responsible for proposing action sequences, which could be SQL queries or Python programs for mathematical reasoning. The discriminator then evaluates the outcomes of these actions, providing feedback to refine the proposed sequences. This framework allows for systematic analysis and comparison of different planning strategies in a controlled environment. In the experimental setup, the focus is on two main tasks: text-to-SQL parsing and mathematical reasoning. For text-to-SQL parsing, the authors used the spider and bird datasets. The entire training splits of these datasets are utilized for prompting or fine-tuning large language models, LLMs. For evaluation, due to resource constraints, 400 samples from spider and 300 from bird are randomly selected. In mathematical reasoning, 500 random examples from GSM-8K's development set are used to test the agent's multi-step reasoning capabilities using the program of thoughts method. The models used in these experiments include CodeLlama 13b as the generator and various LLMs as discriminators, including open-source models like CodeLlama 7b and proprietary models like GPT 3.5 Turbo and GPT-4 Turbo. Fine-tuned versions of CodeLlama 7b and CodeLlama 13b are also evaluated. Figure 3 presents the end-to-end evaluation results and average inference time of our simulation experiments with an oracle. The first row shows that discrimination accuracy closely correlates with the performance of agents across all datasets, regardless of the planning method used. Notably, tree search agents underperform at discrimination accuracy thresholds below 0.8, but show a sharp performance increase at 0.9. Conversely, iterative correction agents require a threshold of 1.0 to outperform re-ranking baselines. The second row indicates that tree search is significantly slower due to frequent Monte Carlo simulations, highlighting an accuracy-efficiency trade-off. Additionally, iterative corrections inference time increases with higher accuracy thresholds, suggesting more iterations are needed for correct answers. This figure underscores the importance of highly accurate discriminators for advanced planning methods and the challenges in balancing accuracy and efficiency. In this section, we explore the impact of discrimination accuracy on language agents using different planning methods. We simulate a discriminator with controllable accuracy using a probability-based threshold tau. For text-to-SQL parsing, we compare the first 5 rows of execution results, and for mathematical reasoning, we compare the predicted Python program's answers with the ground truth. The results show a strong correlation between discrimination accuracy and agent performance across various datasets and planning methods. Specifically, re-ranking agents show linear improvement with increased discrimination accuracy. Advanced planning methods, such as iterative correction and tree search, require highly accurate discriminators to outperform simpler methods. Additionally, we present the intrinsic evaluation results of naive LLMs' discrimination abilities, highlighting the best performance among open-source and closed-source models. Table 1 presents the intrinsic evaluation results of naive large language models, LLMs, discrimination abilities across various datasets. The table highlights that CodeLlama 13 BFT, after fine-tuning, achieves performance levels comparable to GPT 3.5, while GPT-4 demonstrates superior performance across all datasets. Notably, GSM-8K is evaluated using only in-context learning due to the absence of annotated program of thoughts in its training set. The best performance among open-source and closed-source LLMs is indicated in bold. In this section, we discuss the performance of LLM-based discriminators. Initially, we found that most open-source LLMs have mediocre discrimination abilities, as shown in Table 1. To enhance their accuracy, we fine-tuned these models, resulting in significant improvements. For instance, CodeLlama 13 BFT achieved performance levels comparable to GPT 3.5. However, proprietary LLMs like GPT-4 demonstrated stronger discrimination abilities across all datasets. Moving on to observation-enhanced discriminators, we introduced an executability check and incorporated execution results into the models. This led to substantial accuracy gains, as highlighted in Table 2. Specifically, CodeLlama 13b saw improvements of up to 25.4, 30.2, and 8.4 points on Spider, Bird, and GSM-8K datasets, respectively. Finally, in the end-to-end evaluation, we observed that the best performance was achieved with Oracle discriminators, with statistically significant improvements noted. Enhanced discriminators also outperformed their naive counterparts, emphasizing the importance of filtering non-executable programs during planning. Table 2 presents the discrimination accuracy of observation-enhanced large language models, LLMs. The data shows that CodeLlama 13 BFT achieves notable improvements with absolute accuracy gains of 25.4, 30.2, and 8.4 points on the Spider, Bird, and GSM-8K datasets, respectively. GPT 3.5 Turbo also demonstrates significant gains compared to the naive discriminator baseline. The incorporation of environmental observations significantly enhances the model's ability to discriminate between executable and non-executable programs. Table 3 presents the end-to-end execution accuracy results for text-to-SQL parsing tasks. The table highlights the best performance achieved by each discriminator, with the highest accuracy scores in bold. Additionally, the overall best performance for both naive and enhanced discriminators across datasets is underlined. The table also indicates statistically significant improvements marked with an asterisk symbol, which are significant at the p less than 0.05 level according to McNemar's test. These improvements are only observed with the Oracle discriminator, emphasizing its superior performance in these tasks. In the end-to-end evaluation of language agents, we focus on two main areas: text-to-SQL parsing and mathematical reasoning. For text-to-SQL parsing, naive LLM-based discriminators showed poor performance, but enhancing these discriminators with environmental observations significantly improved accuracy. Additionally, these enhancements help reduce end-to-end latency. In mathematical reasoning, iterative correction failed when using naive discriminators, but with enhanced discriminators, performance improved, though no significant difference was found between methods. Error analysis revealed that discrimination errors were prevalent, and advanced planning methods required more thorough exploration to find correct programs before termination. These findings highlight the need for better discriminators and more efficient planning methods. Table 4 presents the average end-to-end inference time per example on the Bird dataset, comparing different discriminators. The table highlights the differences in inference times when using CodeLlama 13b, GPT 3.5 Turbo, and their fine-tuned versions with environmental observations. Notably, the inclusion of environmental observations significantly affects the inference times, particularly for tree search methods. This data underscores the importance of executability checks in reducing overall latency, as well as the trade-offs in accuracy and efficiency when using more sophisticated discriminators. Table 5 presents the end-to-end answer accuracy on the GSM-8K dataset, focusing on different discriminators and their performance in re-ranking and iterative correction tasks. Key discriminators include CodeLlama 13b and GPT 3.5 Turbo, with notable accuracies in re-ranking and iterative correction processes. The table highlights the differences in accuracy when using these models, providing insights into their effectiveness in handling mathematical reasoning tasks. Table 6 provides an error analysis of examples where re-ranking outperforms advanced planning methods. It categorizes errors into discrimination and exploration types, showing that over 50% of errors in each planning method are discrimination errors. Notably, in the Spider dataset, 29 out of 37 errors, 78.4%, are discrimination errors, indicating a significant challenge for discriminators in advanced planning methods. Exploration errors occur when planning methods terminate without finding the correct program, highlighting the need for more thorough exploration strategies. In this paper, the authors investigate the relationship between discrimination accuracy and the performance of planning methods and language agents. They find that discrimination accuracy strongly correlates with the overall performance and efficiency of these agents. However, LLM-based discriminators are not yet accurate enough for advanced planning methods. The study has limitations, focusing primarily on instruction-tuned LLMs and formal language plans, and does not fully explore the generator's impact on planning methods. Future research should aim to develop more accurate discrimination models, extend the study to include other LLMs and natural language plans, and investigate how the generator affects planning methods. Thank you for watching.